At 34,500 feet over the Atlantic, the last operating engine on Air Transat Flight 236 stopped. The Airbus A330 was still 65 nautical miles from the nearest runway. Night covered the ocean below. The airplane carried 306 people, and its electrical system had just fallen back to emergency power. A jet built to cross an ocean had become a glider. The crew had been fighting a fuel problem for almost an hour, but the last flameout changed the problem completely. Hydraulic power, electrical generation, braking, steering, cabin systems, and flight instruments no longer existed in their normal form. Every mile toward Lajes Air Base now came from altitude already stored in the aircraft. The fuel had escaped through one fractured tube. Maintenance had placed that tube beside a hydraulic line it did not match. Then a cockpit indication that looked like an imbalance led fuel from the healthy side toward the leak. The glide began in the engine bay days before the flight departed Toronto. Flight 236 had left Toronto for Lisbon on August 24, 2001. The aircraft was CGS, an Airbus A330-243 powered by two Rolls-Royce Trent 772B engines. Captain Robert Piche was the pilot flying. First Officer Dirk de Jager managed communications, procedures, and navigation beside him. In the cabin were 13 crew members and 293 passengers. The route crossed the North Atlantic and passed south of the Azores. Lajes on Terceira Island was not the planned destination. It was an alternate within reach only because the crew turned toward it before either engine failed. That early diversion created the geometry that later made the glide possible. Nothing about departure suggested that the right engine installation contained a hidden incompatibility. The engine had been changed 1 week earlier. Ground testing had been successful. The airplane had flown for 67.5 hours with the replacement before a small clearance disappeared and two rigid tubes began working against each other. The replacement engine arrived in a configuration Air Transat had not expected. Rolls-Royce service bulletins had changed parts around the rear hydraulic pump. The removed engine and the loaned engine did not embody the same modifications. During installation, technicians discovered that the hydraulic pump interfered with the fuel pump inlet tube already fitted to the replacement. Solving that interference required more than finding a tube that could be bolted into place. The pump, fuel tube, and hydraulic tube had to belong to compatible configurations. The investigation found that a post-modification pump and fuel tube were installed beside a pre-modification hydraulic tube assembly. Together they formed a combination the installation planning had not identified. The lead technician could not access the relevant service bulletin from available computer terminals. He accepted verbal guidance that only one fuel tube needed to be transferred. That shortcut removed a defense, the document that would have exposed the incompatible assembly before the engine returned to service. Technicians achieved visible clearance by applying force while tightening the installation. During inspection, the lines appeared separated, but the hydraulic tube had a natural position, and hydraulic pressure later pushed it back. The small clearance vanished. The two tubes entered hard contact while the engine vibrated in flight. Contact alone did not empty the tanks immediately. Repeated loading damaged the fuel tube until it fractured. The opening developed beside the right engine, where escaping fuel could leave the aircraft without producing an obvious trail visible from the cockpit. The leak began at about 4:38 UTC, while Flight 236 was already far over the Atlantic. This sequence matters because each stage looked acceptable in isolation. A fitted pump, a tightened connection, an inspected clearance, a successful ground run. The failure emerged from how the parts behaved together under pressure and vibration. Static inspection had verified a moment. It had not verified the operating geometry. The first cockpit clues did not say fuel leak. Around 5:03, the crew saw unusual oil indications on the right engine. Oil temperature was low, oil pressure was high, and oil quantity appeared abnormal. Those values were difficult to reconcile. The crew consulted the company maintenance control center, but neither side formed a reliable explanation. The oil readings were not the leak itself. They increased uncertainty around the same engine and consumed attention. Meanwhile, fuel was leaving faster than expected. The totalizer still displayed quantities, but recognizing the rate required comparing what remained with what should have remained at that point in the flight. Automated systems are strongest when a monitored condition matches a defined alert. Here, several values were individually available without being assembled into one unmistakable diagnosis. The cockpit showed pieces of the problem. It did not display a red message saying that a fuel tube had fractured behind the right engine. At 5:33, the imbalance between the wing tanks reached 3,000 kilograms. An advisory appeared and the fuel page came onto the ECAM display. By then, the investigation calculated that about 6.65 tons had already been lost. The leak had been active for 55 minutes before the first fuel-related advisory drew the crew's attention. A fuel imbalance normally describes uneven distribution. One wing carries more than the other. The immediate operational goal is often to restore balance, but imbalance can also be a symptom of fuel leaving one side. Moving fuel before deciding which condition exists can turn a contained loss into a system-wide loss. The A330 did not generate a specific warning for the external leak in this configuration. The advisory required interpretation. The crew had to separate two mental models under pressure. Fuel remained aboard but was unevenly distributed, or fuel was disappearing through an unknown opening. At 5:36, the crew opened the crossfeed valve and switched off the right-wing fuel pumps. That configuration allowed the left tank to feed the right engine. If the right side merely held less fuel, crossfeed could restore balance. If the right side was leaking, crossfeed connected the healthy fuel supply to the same opening. The report found that the crew performed the imbalance procedure from memory and missed a caution directing attention toward a possible leak. Opening crossfeed did not create the fracture. It changed which tanks could reach it. Fuel that had been protected in the left wing now moved through the right engine plumbing and overboard. This is the central contradiction of Flight 236, an action intended to preserve symmetry accelerated exhaustion. The switch movement was correct for one diagnosis and dangerous for the other. The hardware responded exactly as commanded, while the crew's mental model remained incomplete. 12 minutes after the advisory, the crew turned toward Lajes. The diversion at 5:45 was decisive. At 5:48, they told Santa Maria Oceanic Control that fuel shortage was the reason. The airplane was still powered, but the quantities were falling much faster than a normal flight plan could explain. Lajes sits on Tercera Island in the Azores. Its runway and military support made it a practical oceanic alternate, but it was still hundreds of miles away. A direct turn reduced the distance before the engine stopped. Every minute spent continuing toward Lisbon would have changed the later glide from possible to impossible. Diversion did not solve the leak, it changed the endpoint. The route now connected a shrinking fuel supply with one runway. That is why the event cannot be reduced to the final 65-mile glide. The survival geometry was created 41 minutes before the second engine failed. Cabin crew were asked to inspect the wings and engines for visible evidence of a leak. They looked for vapor or condensation behind the wing and nacelle. They saw nothing conclusive. At night, from inside a pressurized cabin, the absence of a visible stream could not prove that fuel remained aboard. The cockpit workload kept rising. Crew members communicated with company maintenance, oceanic control, and the cabin while changing the fuel configuration and preparing the diversion. Each new task made it harder to step back and rebuild the diagnosis from first principles. The report described a narrowing mental model. Once the imbalance explanation had shaped the first action, later indications were interpreted around it. This was not carelessness. It was the interaction of ambiguous automation, unfamiliar symptoms, procedural memory, time pressure, and a system losing fuel faster than the crew had ever encountered in training. The trim tank added another complication. About 3.2 tons stored in the tail transferred forward automatically. That fuel entered the wing system and then became available to the leak. The transfer delayed the fuel advisory by about 15 minutes because it temporarily supported the displayed wing quantities while total fuel continued disappearing. Automation was performing a normal center of gravity function. It had no knowledge of a fractured line near the right engine. A transfer that normally improves efficiency therefore extended the period in which the leak remained hidden from the crew's most salient warning. Flight 236 shows why system behavior must be read in context. Every automatic action can be locally correct and globally harmful when the system boundary has been breached. The trim transfer, crossfeed, and engine feed logic all operated as designed. None could determine whether fuel leaving a tank was reaching combustion or the atmosphere. By 5:45, fuel on board had fallen to about 8.7 tons, with roughly 9.3 tons already lost. The leak rate was not a small planning error. It was large enough to empty an intercontinental aircraft while the engine still ran normally. The right engine continued converting some fuel into thrust, while a separate path discharged the rest. With crossfeed open, the leak no longer respected the boundary between wings. The left tank's faster reduction was evidence that its fuel was crossing the aircraft, but cockpit indications did not package that evidence as one urgent instruction. The crew saw quantities, advisories, and engine pages while managing a diversion across oceanic airspace. The safest remaining resource was time. Fuel could not be recovered. Distance to Lajes could only be reduced by continuing the diversion. The airplane was now in a race between geographic progress and a loss rate that the crew could not directly measure. At 6:13, the right engine stalled and flamed out. Flight 236 was near flight level 390 and about 150 nautical miles from Lajes. The engine nearest the leak stopped first because its local supply had reached exhaustion. Only the left engine remained. The first flameout forced a reassessment. The crew declared the emergency more explicitly, descended, and prepared for the possibility that the remaining engine would not last. Fuel displayed in the left side was now the only source of powered flight, but the crossfeed history had already exposed much of it to the leak. A twin-engine airliner can fly safely on one engine when fuel and systems remain available. This was different. The remaining engine was not preserving a stable one-engine condition. It was consuming the last accessible fuel while the aircraft moved toward an island still beyond normal visual range. 13 minutes later, at 6:26, the left engine failed. Flight 236 was about 65 nautical miles from Lajes at roughly flight level 345. The crew completed the all-engines flameout procedure and established the best descent profile they could toward the island. Emergency electrical configuration stripped the cockpit to essential loads. The ram air turbine deployed into the airstream to provide limited hydraulic and electrical support. Cabin lighting fluctuated. Public address capability became unreliable. The airplane remained controllable, but control now depended on a much smaller set of systems. The second flameout converted altitude into a measured budget. Descend too steeply and the runway would fall beyond reach. Hold too much altitude and arrive high over the island with no engine power to correct. The crew needed the right path in 3 dimensions, at night, without a second attempt. An airliner glide is not a fall. Forward speed drives airflow over the wings, and the aircraft exchanges altitude for distance. The useful ratio changes with weight, configuration, wind, speed, turns, and contamination. The crew could not simply divide 34,500 feet by 65 miles and assume the runway was guaranteed. Lajes controllers used radar vectors to reduce uncertainty. They could see the aircraft relative to the island and provide headings. The crew still had to decide how much altitude to spend on each turn. Banking increases lift demand and drag. A wide correction can consume miles that no engine can restore. The published record makes the outcome look like a straight line from flameout to runway. In the cockpit, it was a sequence of continuously revised energy decisions: speed, heading, descent distance, wind, runway alignment, and the need to arrive low enough to land but high enough to reach concrete. In the cabin, the emergency changed from diversion to possible ditching and then back toward a runway landing. Flight attendants prepared 293 passengers while normal systems degraded. Instructions had to remain simple enough to survive noise, fear, changing lighting, and unreliable public address. Cabin crew secured the space, reviewed brace positions, and prepared exits. 3 Portuguese-speaking attendants improved communication with many passengers. The crew did not know whether the airplane would reach Lajes, whether landing gear and brakes would behave normally, or whether evacuation would begin on a runway or in water. Human preparation is an engineered system too. It converts an uncertain future into actions people can perform immediately. Belts tight, loose objects secured, brace command understood, exits assigned, and authority clear. Those actions do not change glide distance, they change what happens after the glide ends. Flight 236 approached Terceira, with more altitude than a normal powered arrival. That was preferable to arriving low, but excess energy now had to be removed without thrust reversers available in advance, and without the option to climb away. The crew used turns and configuration changes to manage the approach. Landing gear adds substantial drag, flaps change lift and drag while reducing the speed required for landing. Extending either too early spends glide range. Extending too late leaves a fast, high aircraft with little room to stabilize. Each configuration change therefore belonged to a specific point in the approach. Lajes provided runway 33, airport rescue vehicles, and visual conditions good enough for the final segment. The night landing was still an engines-out visual approach in an aircraft whose systems had been reduced to emergency essentials. At 6:45 UTC, 19 minutes after the second engine stopped, Seagits touched down on runway 33. The aircraft arrived fast and hard. With normal braking support degraded, tires failed, and the landing gear absorbed loads far beyond a routine arrival, the airplane remained on the runway. Small fires appeared around the left main gear wheels after it stopped. Rescue vehicles were already positioned and extinguished them. The captain ordered evacuation. One exit jammed, slowing part of the flow, while slides at other exits carried people away from the aircraft. 16 passengers and 2 cabin crew were injured during the evacuation. There were no fatalities. The distinction matters. The flight ended successfully, but success did not mean without damage or injury. It meant the chain stopped before fuel exhaustion became an ocean impact. The aircraft structure and main landing gear were damaged. The tires and wheels recorded the energy of a landing made without normal propulsion, yet the fuselage remained in occupied survival space until everyone could leave. CG-ETS was later repaired and returned to service. Photographs after landing show an intact A330 surrounded by emergency activity, not a wreck scattered across terrain. That visual can obscure how narrow the margin had become. The airplane had crossed an oceanic distance with a leak, then flown the final 19 minutes with no engine producing thrust. The safe landing depended on layers that did not share one origin: an early diversion, available altitude, an island runway, radar assistance, emergency systems, cabin preparation, flight crew coordination, and precise manual control. Remove one layer and the same initiating fracture could have produced a different ending. Investigators found the physical explanation around the right engine. The fuel tube had failed where it contacted the hydraulic line. The combination of parts traced back to the engine change. This evidence connected a maintenance configuration decision directly to the initiating leak. The report did not stop at the technician who tightened the connection. Engine receipt and planning had not identified the configuration differences. Access to service bulletin information failed. Verbal guidance replaced document review. Post-installation quality checks did not specifically require verification of the pump, hydraulic tube, and fuel tube combination. A durable causal account therefore spans hardware and organization. The tube fractured physically. The mismatch existed because information about modification status did not reliably reach the people assembling the engine. The inspection missed it because the system asked whether the installation looked acceptable, not whether every related part shared the correct configuration. The report's causal findings describe a precise combination. The replacement engine was in an unexpected pre-service bulletin configuration. The operator had not previously encountered that arrangement. A post-modification hydraulic pump and fuel tube were installed with a pre-modification hydraulic tube assembly. The relevant service bulletin became known during the work but was not reviewed. Force used to create clearance did not produce a stable operating clearance. Hydraulic pressure returned the tube toward its natural position. Contact followed, then fracture, then leak, then exhaustion. None of those statements requires a dramatic hidden defect inside the engine core. The failure developed an external plumbing whose compatibility depended on configuration control. That makes the event broadly relevant. Complex machines are not collections of interchangeable parts. A component can fit its attachment points and still be wrong for the surrounding system. Investigators also examined why the crew did not diagnose the leak before both engines stopped. A large imbalance was rare, but its presentation was an advisory rather than an unambiguous critical warning. The crew had not experienced a comparable fuel leak in operations or training. Procedures treated imbalance and leak as related possibilities without making the distinction immediate. Once crossfeed opened, cockpit activity increased sharply. The crew navigated toward Lajes, coordinated with controllers and company maintenance, inspected the cabin view, monitored unfamiliar oil indications, and managed falling quantities. High workload left little capacity to reconsider the first diagnosis. The report's language is important. It does not excuse the missed procedure, and it does not reduce the event to pilot error. It identifies a human-machine system in which alert design, checklist structure, training, workload, and memory all influenced one action with system-wide consequences. Fuel quantity was not hidden. The problem was turning quantity into meaning. A total can look plausible until it is compared with flight plan expectation, elapsed time, and engine consumption. The report noted that the crew did not identify the higher-than-normal reduction before the imbalance advisory. This is a monitoring design problem as much as a calculation problem. Humans are poor at detecting slow change when the reference value is not continuously visible. A system that shows current fuel but does not clearly show expected fuel can make a major loss resemble an ordinary number. After Flight 236, the relevant safety work focused on leak procedures, indications, training, maintenance compatibility, and recorder preservation. The objective was not to ask future crews to perform mental arithmetic faster. It was to make the abnormal pattern easier to recognize before action exposed protected fuel. The investigation issued recommendations across maintenance and operations. Configuration parity needed to be established before engine installation. Clearances between fuel and hydraulic lines needed explicit inspection. Service information had to be available to technicians when configuration differences appeared. Operational recommendations addressed major imbalances, possible leaks, training, and automated fuel transfers. A significant imbalance should trigger deliberate leak assessment before crossfeed exposes additional tanks. Procedures and training needed to represent the scenario the Flight 236 crew actually faced. Ambiguous indications, no direct warning, and a rapidly changing fuel picture. These changes share one principle. Safety should not depend on one person recognizing a rare combination from memory. The system should preserve defenses through planning, documentation, physical inspection, alerting, procedure design, and recurrent training. Recorder evidence had limits. The cockpit voice recorder overwrote 90 minutes because it continued running after the landing. Only 2 of 3 relevant circuit breakers were pulled, and clear instructions for preserving the recorders were not readily available to the crew. That loss did not prevent investigators from establishing the physical and operational chain. Flight data recording, maintenance records, fuel calculations, component examination, controller records, interviews, and surviving audio supported the reconstruction. But the missing voice period reduced insight into how the crew interpreted the early indications. Evidence preservation is another defense that begins before an accident. A recorder can work perfectly during flight and still lose the most useful period if power remains applied afterward. The lesson is procedural. Preservation must be simple, known, and possible under post-emergency workload. The captain's control of the engine's outglide prevented a catastrophe. The first officer provided effective support throughout the descent and landing. Those are explicit findings in the report. Their performance after total power loss deserves recognition without turning the earlier diagnostic failure into a footnote. The crew misread the fuel situation and took an action that worsened the loss. Later, that same crew diverted early enough, managed a powerless wide body at night, coordinated with controllers and cabin crew, and placed it on a runway with everyone alive. Forensic analysis is weakened when it demands heroes or villains. Complex accidents are sequences. Human performance can be flawed in one phase and exceptional in the next. Safety improves by understanding both, because future systems must reduce the first vulnerability while preserving the skill and coordination that produced the recovery. The 65-mile number is memorable because it compresses the emergency into one impossible-looking distance. But distance alone did not save Flight 236. The aircraft began that glide high enough, close enough, and already pointed toward the right island. Controllers reduced navigation uncertainty. Emergency systems preserved control. The crew managed energy well enough to arrive, nor was the glide free of consequence. Landing gear and structure were damaged, tires failed, fires began near the wheels, and 18 people were injured during evacuation. The final runway image represents survival, not normality. The more useful measure is not a record claim. It is the number of independent conditions that had to remain true after fuel reached zero. Flight 236 survived because the failure chain was matched by a recovery chain. At the center of the event is a small incompatibility with a large reach. 2 tubes touched, 1 fractured, fuel left one side. Crossfeed exposed the other side. Engines stopped. A wide body glided toward an island. Each step follows from the previous one, but none was inevitable before the chain formed. Configuration control could have stopped it. Service bulletin access could have stopped it. A stable clearance check could have stopped it. A clearer leak warning or a procedure consulted before crossfeed could have limited it. An earlier comparison of actual and expected fuel could have exposed it. Accidents become understandable when their scale is reduced to these transitions. One tube does not automatically bring down an aircraft. The danger grows when separate defenses describe different versions of the same physical system, from a part number on the ground to a switch selection over the ocean. Flight 236 reached Lajes because the crew turned before the fuel was gone and flew precisely after the engines stopped. Investigators then traced the empty tanks back through cockpit decisions, system indications, maintenance records, and finally to incompatible plumbing beside the right engine. The finished account is neither a simple pilot error story nor a simple mechanical failure story. It is a configuration failure that produced ambiguous evidence, followed by a diagnostic action that expanded the loss, followed by an exceptional recovery using the altitude and geography still available. A safe system makes the hidden physical state easier to see before the correct action, and the dangerous action look identical. When it fails to do that, survival may depend on what remains after every planned source of power is gone.